in our last class I discussed the operation of a flyback converter. The flyback converter is nothing but an isolated buck boost converter. Okay. The input output relationship is same as a buck boost or a Chook converter. In addition, there is a term, the turns ratio, N2 by N1. Now, because of this N2 by N1 turns ratio, the magnitude of V0 and VDC can be greatly different. Okay. What is the principle of operation? Though there is a transformer, only one winding is carrying current at a time. So, close the switch, energy is stored in Lm, where Lm is the magnetizing inductance. Open the switch, stored energy is transferred to the load. Okay. So, remember, though I am using a transformer in flyback, current drawn from the source is the magnetizing current only. Okay. Because in some of the power supplies operation is going to be different. So, that is one of the reasons the flyback converter is very attractive for low power range. Generally, if the power rating is of the order of 200 watts, flyback converter is a very good option. Okay. I told you that invariably flyback converters are operated in discontinuous mode. In other words, we are resetting the flux completely, because operation is always in the first quadrant of BH characteristics. Okay. So, if there is a finite current flowing in the secondary, in other words there is some finite flux in the core. So, when you close the switch in the next cycle, and in case the value of D has increased, it may so happen that core may get saturated. Okay. So, if it gets saturated, you may be able to see the smoke coming out from the flyback converter or a black box. Okay. How do you avoid this? One way to have an air gap during the transformer fabrication. Okay. So, if I have an air gap, there is going to be a leakage flux. So, when I open the switch, you may be providing a path for the magnetizing energy or magnetizing current, but then there will be a spike due to the leakage inductance. So, we need to change the power circuit configuration. So, that is why you try to solve one problem, try to avoid the saturation of transformer by providing an air gap. The moment I do that, it gives another problem, leakage flux. So, that is why if you try to solve one problem, another problem is created. It is almost similar to a law of conservation of energy. Energy can neither be created nor destroyed, it can be transformed. Similarly, sorrows, you cannot destroy them nor create them, you can transform them from one form to another form. Here also, you had a problem, try to solve one problem, it gave rise to another problem. Yeah, coming back to flyback converter, the another major advantage of flyback converter is we can have multiple outputs. And one point I forgot to tell you in the last class is that closed loop operation is a must. Like any boost converter or Chook converter or whatever, closed loop operation is a must here. Why? Because I am storing the energy, dumping it to the output. So, accidentally load gets disconnected, capacitor voltage goes on building up maybe. Okay. So, closed loop operation is a must. Now, coming back to, we also discussed the forward converter, which requires a 3-winding transformer. See in this figure, N1, N2, N3. Okay. See the dotted terminals here. So when I close the switch, current enters the dot. So in the secondary, current can leave the dot. So I2 starts flowing when I close the switch, but then that cannot happen in the tertiary winding because of this diode connection. Okay. So the primary current here is the sum of the equivalent secondary current plus the magnetizing current. Okay. When I open the switch, magnetizing current has to be continuous. In addition, the inductor current should be continuous. Okay. So this current can be made continuous by connecting a freewheeling diode here. So inductor current starts flowing through DF when I open the switch. Okay. So the magnetizing current starts flowing through this winding. So operation of these two branches, the primary and the tertiary, is same as that of a flyback converter. Okay. Current enters the dot. So direction of flux should be the same. So here also current enters the dot. Current enters the dot. Okay. So for a non-ideal transformer, okay, which is used in a forward converter, we require three windings. Okay. So this is nothing but an isolated buck, because this entire structure, this part is nothing but a buck converter. Okay. Forcing function here is the reflected voltage, the secondary. The primary is being connected to VDC, so secondary is VDC divided by N1 multiplied by N2. So that is the forcing function, and the operation is similar to a buck converter. So transfer function is VDC into N2 by N1 multiplied by the duty cycle. Okay. So what is the voltage that is appearing across D3 when the switch is on? So in this circuit, voltage applied to the primary is VDC with the dot as positive. So this is positive. So this terminal voltage induced in this one is going to be negative, and it is magnitude is VDC divided by N1 into N3. So this is positive, negative, and I have a source VDC. So equivalent circuit is something like this: VDC into N3 by N1 in series with VDC is a voltage that is appearing across D3. Okay. So diode should be able to withstand this voltage VDC plus 1 plus N3 by N1. Okay. So open S, magnetizing current starts flowing through the tertiary winding. Voltage applied to the tertiary winding is VDC. Okay. So what is the voltage that is appearing across the switch and the diode that is connected in the secondary? This is a D2. Okay. Same, you need to use the transformer principle. If I know the voltage applied to one winding, so voltage induced in the secondary is voltage winding induced in another winding is just depends on the turns ratio. None. Okay. But then what is the magnitude of current that is flowing through the tertiary winding? Okay. Just prior to opening the switch, the magnitude of the magnetizing current is VDC divided by Lm into D into T. VDC by Lm is the slope of the rate of rise of magnetizing current, dt is the duration for which the switch is on. So the peak value is VDC divided by Lm into d into t. Okay. So when I open the switch, the current gets transferred to the tertiary having N3 number of turns. So peak value of the current that is flowing in N3 is Im into N1 divided by N3. Okay, because Im is the peak current that was flowing in N1 turns. Now that current gets transferred to N3 coil, or the coil which is having N3 number of turns. So this is the peak value of current that is flowing through the diode and the tertiary winding. Now voltage applied to the tertiary winding is VDC. So voltage induced in the primary is VDC multiplied by N1 into N3. Remember, when N3 is carrying current, d phi by dt is negative, d phi by dt is negative, flux is decaying now. So this is the equivalent circuit. So voltage across the switch is the sum of these two, VDC plus VDC into N1 plus N3 is the voltage across the switch. Okay. What is the voltage that is appearing across diode D2? Okay. Voltage is same principle, voltage applied to the tertiary winding is VDC. So voltage induced in the secondary is VDC divided by N3 multiplied by N2. Again d phi by dt is negative. Okay. So this is the equivalent circuit, the voltage induced in the secondary. DF is conducting. When I open the switch, because of LF, DF is conducting, freewheeling diode is conducting, voltage across the D2 is only VDC into N2 by N3. Okay. So the transfer function between the input voltage and the output, it depends on N2 and N1. Now how many number of turns should be there in the tertiary winding? Okay. How do I choose the number of turns in the tertiary winding? By the way, what is the purpose of providing a tertiary winding? It is for the continuity of flux. Okay. What is the condition? Flux in the core should become 0 just prior to closing the switch again in the next cycle. Okay. Invariably, even forward converter, we need to operate in discontinuous mode of operation. Discontinuous mode of operation, again same concept as that of a flyback converter. Discontinuous current in the sense flux in the core is 0, or in other words we are completely resetting the flux in the core. Okay. Now let us see what should be the number of turns that are required in N3. So peak value of current, magnetizing current Im that is flowing in N1 turns is VDC divided by Lm into d into t, that is the peak value of current that is flowing. Now when I open S, that current gets transferred to the tertiary. So this value of current is Im into N1 divided by N3. So here is the equivalent circuit. See, when I close the switch, Lm starts flowing. When I open the switch, it starts flowing through diode D3 and this is the voltage. Now VDC into N1 and N3, this is the voltage referred to the primary. Okay. So when I close S, d phi by dt is positive or flux increases. So it is given by VDC divided by N1 into d into t, volts second per turn, volts second per turn. Okay. Now what is decrease in flux or d phi? It is VDC divided by N3 and Ta is the time for which D3 conducts, or this is the time Ta. Okay. Because for continuity of flux, or continuity of flux is being provided by tertiary winding. Okay. So at steady state, increase in flux should be equal to decrease in flux, or if it starts from 0, it should reach 0 at Ta. So I will equate it, I will find that Ta is equal to N3 divided by N1 into d into t. Okay. And for discontinuous conduction, Ta should be less than 1 minus d. Okay. I will repeat, for discontinuous conduction, Ta should be less than 1 minus d, because dt is the time for which the switch S is conducting. The remaining time 1 minus d into t is for which, if the current is continuous, D3 will conduct. For discontinuous conduction, so Ta should be less than or equal to 1 minus d into t. Okay. So if d is equal to d max, this is the relationship. Okay. I will choose N1 is equal to N3, number of turns in both the windings is the same. So I will find that maximum value of d is 0.5, maximum value of d is 0.5. So in a forward converter, if the number of turns in the tertiary and the primary is the same, the maximum value you can go is 0.5. Can you go, or is it possible to go above 0.5, or what happens if I increase d above 0.5? So this is the situation. When I close S, rate of rise of current is determined by Lm, voltage applied is VDC. So slope of this line is VDC divided by Lm. Okay. I will open the switch. See here, current starts flowing in tertiary winding. Number of turns is the same. Okay. Voltage applied is also the same. Okay. So this voltage increases the flux. This voltage, because of this voltage, flux decreases. Okay. And magnitude of both the voltages is the same. So if this switch is on for a time which is greater than the time for which diode is on, I will repeat, if the switch is on for a time which is greater than the time for which this diode is on, flux will not become 0 when I close the switch for the second time. Okay. Because rate of rise is the same, rate of fall, the slope is also the same, but then on time is higher than the off time. So there is going to be some residual flux. Okay. See here, if the flux is being completely reset, we have something, this sort of a situation. Flux becomes 0, it will start from here. So when I close the switch for the second time and assume that same value of D has been maintained, now magnitude of flux that is flowing in the core is higher than, or this value is higher than this, okay, because D has been not changed, D has been kept same. So when I open the switch for the second time, again this point is higher than this, okay, and if you continue, it may so happen that core may get saturated, or core will get saturated, because you will have some sort of a build up process of the flux, because time for which in this circuit, just see, time for which S is on is higher than the time for which the diode is on. So this is positive D phi and this is negative D phi. Flux increases, flux decreases, flux decreases. Now voltage applied is also same, number of turns in both the windings is also same. So I can have a just continuous conduction with the D is equal to 0.5. So for D is equal to less than 0.5, you will have a discontinuous conduction, and if you go D is equal to, and if you go D above 0.5, you may end up with saturation, okay. Now let us draw the waveforms for a forward converter. Now let me tell you one thing, I think I have not drawn the waveforms for a flyback converter, okay, but then I have drawn all the waveforms when I was discussing the recovery of trapped energy. So both are the same. So I would expect you to go back and draw the various waveforms for flyback converter. Principle of operation is the same. So we'll draw. Now forward converter we will draw. S is on, and in this period DF, the freewheeling diode and D3 are on, they may be on. If the flux becomes 0, so D3 is on till here, okay, and I told you that this part can be approximated to a current source and expect that IL to be continuous, so in the entire this period, or from dt to t, D3 is assumed to be on. See, IL increases when I close the switch, because voltage that is induced here is VDC divided by N1 into N2, see here, okay, diode D2 is on, nothing but a buck converter, okay, current increases when I open S, so load current starts flowing through DF and it is assumed to be continuous, okay. So DF is on for the entire off period of the switch S, but then D3 it conducts only for a finite duration, okay. So voltage applied to the inductor when the switch is on is VDC into N2 divided by N1 minus V0. This is the voltage applied to the inductor LF, and when the switch is opened, since DF is conducting, voltage applied to LF or this inductor is minus V0. So by equating you will get the transfer function. When I close S, inductor current is same as I2, IL is same as I2, okay. We said that I2 is increasing, so this is the waveform for I2, okay. Why it starts from a finite value? It's because just prior to closing the switch in the next cycle, current through DF was finite. So this is the current that was flowing through the diode DF just prior to closing the switch S. So this current starts flowing through D2. Okay. Open the switch, D2 becomes 0. Okay. And this current jumps to or starts flowing through DF. So this is the current waveform. Actually this magnitude should be equal to this magnitude. How does I1 look like? I1 has two components. I1 has two components. One is the reflected secondary current and the magnetizing current. Okay. We are assuming that Im has become 0, in the sense we have completely resetted the flux. Okay. So Im starts from 0, but then I2 prime is non-zero, it is finite, because we have connected an inductor in the load circuit. In other words, load can be represented by a current source. I told that current increases and decreases, and it is and just prior to closing the switch S, current that is flowing through DF is finite. So that current starts flowing through I2. So I2 dash is a finite quantity. Okay. So the primary current, see Im starts from 0, this is, and varies linearly, and this dotted line is I2 prime, okay. The sum of these two is the primary current. Okay. See, because I2 is finite, so I2 prime is again finite. So this is I2 prime, Im, and this is I1. Okay. And this peak value of Im is VDC divided by Lm into D into T. So when I open S, this current or flux has to be continuous. Continuity of flux is being provided by the tertiary winding, it gets transferred here. So Im into N1 divided by N3 is the peak current that is flowing through the tertiary winding. Voltage applied is VDC, and L3 is the inductance of the coil N3, having N3 number of turns. Okay. I've taken here some arbitrary number of terms, N3. Okay. I have not assumed N1 is equal to N3. I have not assumed N1 is equal to N3. So slope here is L3, because it is flowing through a coil having N3 number of turns. Okay. And see the various voltage waveforms. S is on, this is on. So voltage across the switch is VDC plus this quantity. Okay. When diode D3 is conducting, what happens when D3 stops conducting? What is the voltage that is coming across various devices? Flux is 0, no current is flowing in any of these windings, primary, secondary, tertiary. Okay. So you cannot use the transformer action principle. Okay. So entire VDC is blocked by D3 diode here. Okay. Because no current is flowing in this coil. Similarly here, the entire supply voltage is blocked by the switch S, it appears across S. Okay. So it's very simple here, tertiary and primary voltage, these are VDC. What happens in the secondary? Diode is conducting, okay. So DF is conducting. So voltage appearing across N2 turns is the voltage across the diode D2, but then there is no current flowing in these two windings, so there is no voltage here, okay. If one of them were to carry a current, there would have been a reflected voltage or induced voltage. Now no current is flowing, so there is no relationship at all, so there is no voltage induced in this coil, no current in this as well as this. So in practical it is a zero voltage that is appearing here, zero voltage, because this is this point, okay. So see the waveforms here, VDC, that is voltage across the switch. Similarly D2, when the diode DF is conducting, it is VDC divided by N3 into N2 and it is 0, and similarly voltage across the switch or voltage across D3 is this waveform, and it is 0 when it is conducting, and when current has become 0, voltage across jumps to VDC, okay. So if the current is just continuous or if the flux is just continuous in the core, okay, so you will not have this jump, that is only the difference, you will not have this jump. If the flux is just continuous, you will not have this jump at all, okay. And this is the voltage appearing across the freewheeling diode DF, okay. So when it is conducting, voltage across it is 0, and when it is off, voltage across it is voltage induced in the secondary winding itself. See here, D2 is conducting, so voltage induced in N2 is a voltage appearing across the diode DF, okay. So this is a short here, voltage across N2 induced in N2 is a voltage across DF. This is nothing but VDC divided by N1 into N2, okay. So these are the various waveforms for a forward converter using 3-winding transformer. Now let us discuss some special cases in forward converter, okay. So far we discussed the forward converter wherein the tertiary winding is connected to the supply voltage VDC, the same voltage that is being applied to the primary or the having coil N1 number of turns, and I told you that N1 and N3 they form a flyback connection. You do not have to connect the third coil to the same supply voltage. The purpose of the third coil is just to provide the flux continuity, nothing else. So instead of feeding the energy stored in the magnetizing branch to the source, you can transfer it to a capacitor and a load, nothing but a flyback converter. See something like this, N3 coil, diode D3 and C and R. This is nothing but a flyback converter. I have not shown the primary here, primary does exist, okay, primary does exist, because see here in the previous, see this current is entering the dot here, current is entering the dot in the primary. So for a flux continuity in the tertiary, current also should enter the dot, current also should enter the dot, okay. So see here, current is also entering the dot. So I connected D3 with this, so capacitor voltage polarity is this is positive, this is negative. So I can have one forward and one flyback converter, okay. So here the V0 is, again you can use the transfer function that we derived for flyback converter, please, you because principle is the same. Okay. Again, you need to find out when the flux becomes 0. If it is just continuous, you use the same transfer function that we derived for the flyback converter. So, you do not have to connect the tertiary winding to the same source. You can have a flyback converter in a forward converter itself. By the way, why are we using a third winding? What if I do not use a third winding using a non-ideal transformer? In an ideal transformer, I told you that you do not require the third winding because reluctance is 0, mu r is infinity, so ampere turns required to establish the flux in the core is 0, so there is no magnetizing current. So you do not require a tertiary winding. Now I will use a non-ideal transformer wherein there is a finite magnetizing current, but I will not use the third winding, and I will do some modification. Let us see what happens. See here, this is what I have done. Let us see what happens, whether it will work, or if it works, what is going to happen. Okay. I have not connected or not used D2 here, there is no D2. Okay. So when I close S, okay, close S, what happens? Current is entering the dot, current can leave the dot in the secondary. Okay. Of course, DF is reverse bias, current starts flowing here, IL starts increasing, IL therefore I2 starts increasing. I1 does have a component of magnetizing current. Magnetizing current is still there, it is a non-ideal transformer. I2 prime plus Im. Okay. So this is the primary current. Opening the switch after dt, what will happen? Flux must be continuous, and second is the inductor current IL should be continuous. Okay. Now for the continuity of flux, the correct direction for the current in the secondary is to enter the dot. See, I will repeat. When I close the switch, I1 enters the dot, the correct direction in the secondary is to leave the dot. It is possible because there is no D2. I will open the switch after dt. Okay. I2 becomes 0, but then magnetizing current has to be continuous. Now that can be made continuous by suitable current that is in the secondary. What is the correct direction for the current that is flowing in the secondary? If current is entering the dot in the primary, when I open the switch, current must enter the dot in the secondary. I will repeat, see here, current was entering the dot, okay, and current is leaving. This is perfectly a transformer action now. Okay. I will open the switch, magnetizing current has to be continuous, so it is entering the dot. Now current starts entering, or current should enter this terminal. So the equivalent circuit is here. So this is the path, this is the path, and this current also should be continuous. So DF carries the magnetizing current as well as the inductor current IL. Of course, it is a reflected magnetizing current. See, this is the equivalent circuit. Close S, IM starts flowing, I2 prime also starts flowing because there is nothing here. Okay. Open S, IM will starts flowing through this branch. IL also starts flowing through this branch. Okay. So, in a 3 winding case, since I used D2 in the secondary, that cannot happen there, because reverse flow of current is not possible in a diode. No. Okay. So, I have not used D2. Now, I2 or the equivalent magnetizing component of current can flow in the secondary. It should enter the dot, and it tries to enter the dot and it flows. But then what happens to the rate of decay of flux? See the equivalent circuit here. I am connecting a diode across an inductor. Okay. If the resistance is 0, what will happen to IM? Ideal diode is also ideal, this coil is also ideal, no R, IM will remain constant. Whatever that was there, that was flowing through the primary winding, it gets transferred and the magnitude will remain constant. In the sense, it will not decay, it will not decay. Now, if there is a finite resistance, it starts decaying slowly, because whatever the stored energy is dissipated as heat in the winding resistance and maybe internal resistance of diode DF. So, very slow decay. So, when I close the switch for the second time, maybe after some time, there is a finite flux and rate of decay of flux is very slow. It may so happen that core will saturate. So, when I use a 3 winding transformer, I am using a negative voltage across LM. See here, see in the previous, see here, the negative voltage is applied across LM. So, decay is faster, Now, here decay is very slow, Maybe sometimes just the opposite that what we did in AC to DC conversion. In the very first lecture in AC to DC, when I introduced the concept of freewheeling, I said that you have to maintain some current in the load. Okay, if there is no freewheeling diode, voltage that is appearing across the load becomes negative beyond pi. I repeat, because beyond pi the input voltage becomes negative. So, if I apply negative voltage to a load which is RL, rate of decay is going to be faster. So, I want to reduce the rate of decay. So, I said I will apply a 0 voltage, in other words I will connect a freewheeling diode. I have told this in the very first lecture of AC to DC conversion. So, if you apply a negative voltage, decay process is going to be faster. If I apply a 0 voltage, decay is very slow. Okay. Maybe just the opposite that is required here. I want to reset the flux in the core, because again unidirectional excitation operation is always in the first quadrant. So, rate of decay is very slow, and it may so happen that in the second cycle core will saturate. Okay. What is the third case? What is the third case? A third interesting case is there is no LF at all. Don't use LF. Don't use LF. Okay. Don't use LF. Now, just because we had used LF, we connected a DF here, because when I open the switch, this current has to be continuous, so it will start flowing through DF. So if there is no LF, you may not even require this DF, but then what will happen? Okay. So in this circuit, there is no LF, there is no DF. Okay. Close the switch in the primary, current enters the dot, current leaves the dot. So this capacitor gets connected across the secondary, because this is not there, even L is also not there. So when diode is on, so this gets connected to the secondary. Okay. So we have a case something like this: primary, a voltage source of VDC, secondary, I have another voltage source of some other magnitude V0, and waveforms of VDC may not be the same as waveform of V0. So I have a case wherein the transformer, both sides of a transformer, I have connected two voltage sources. I do not think you can have this sort of a situation. Wherever, even in AC supply, I connect a source to the one of the winding, second winding is connected to the load. We do not connect two voltage sources of two different waveforms to the transformer. Okay. So if I do that, it may affect the power transfer or energy transfer. Okay. So I should not allow the capacitor voltage to appear directly across the secondary turns when the switch is on. Okay. So I use a inductor. Okay. So since I am using an inductor now, current has to be continuous, so I use a freewheeling diode. So that is how we have reached to this stage. We should not allow the capacitor voltage directly to appear across the secondary when primary is carrying current. So you connect an inductor here. If you connect an inductor, this current has to be continuous, so use a diode DF here. So that's it about the forward converter. Generally it is used for wattage above 200 watts, from 200 to approximately 5 to 600 watts. This could be more also. Okay. But then as the power rating increases, the trend is to go towards a forward converter. Now you may be able to reason it out. What could be the reason? What could be the reason? What happened in flyback when I close the switch, and what happens in a forward converter when I close the switch? In a flyback converter, we are storing the energy in the magnetizing inductance, transferring it to the load. Source current is only the magnetizing current. What happens in a forward converter? Source current is the sum of magnetizing as well as the equivalent load current. Okay. So maybe very obvious, there only magnetizing energy, store it and dump it. Here source supplies equivalent current, or source supplies power directly to the load here. So when I close the switch, there is an equivalent current in the primary. So as the power rating increases, so the size of the transformer that is required in a flyback is going to be high. It increases. So that is one of the reasons to go towards the forward converter for high power range. More about it we will see later in the next class. Thank you.